Hello, everyone. Thanks to be here for my thesis defense. I'm so glad to be in front of you today to present my work I done during this thesis. So my thesis title is Distributed and Parallel Computing for Very Large Neural Networks. This thesis is realized with the University of Paris-Saclay. My academic supervisor is Professor Naïd Emad, and my academic supervisor is Dr. Chong Yi here. And we are at the Maison de la Simulation for this defense. So to present my work, I divide my presentation in three main parts. In the first part, we will see together the context, the motivation, and the objective of this thesis. After that, we will see together my different contributions during my 3 years of thesis. The first contribution is about graph neural networks. The second one is about matrix representation, the concurrence matrix representation. And on the third part, we will see, I will present a new embedding initialization based on spectral method. And we will finish with the conclusion. Okay, so let's start with the context and motivation. So deep learning have been a revolution in the last few years, thanks to two main keys. The first one was the big data. It helped us to capture the information to be able to train and learn from models. And this is, we can build new algorithms thanks to an increase of computation power, especially thanks to special hardware accelerators, specially designed for AI tasks. And these two, the convergence of these two tasks can create the emergence of advanced algorithm. We have built a new model, new algorithm, new architecture to be able to apply deep learning model on a wide range of application and with different type of data structure. So all of this environment create the emergence of AI generative model, large AI generative model. One very famous one is the large language model. A large language model is a model specially designed to answer to NLP task. And today, one model is used on different type of tasks, a multitude of tasks. For example, for code generation, language translation, or text generation. And to be able to answer to this multitude of tasks, this type of model need to be large to be able to generalize. And this need of generalization have created an actual increase of number of parameters in last few years. For example, in 2019, the most important model was GPT-1, where the number of parameters is around 100 million parameters. And today, the most biggest models are more around 1 trillion parameters. And to be able to train this model and to be able to get a good accuracy with this model, you need a lot of computation power to train them. And so, for example, to be able to train the GPT-4 model, this one, the largest one, we require to use more than 25,000 GPUs during more than 3 months to be able to train this model. So solution must be found to reduce the execution time, the training cost associated with this deep learning model. So large language have several challenges, create different challenges. The first one is, of course, the model complexity, because when the size of the model becomes very important, you need a lot of computation power to train this model, to tune the model so that it will be able to make prediction. We have also some challenge around data, because sometimes we need to deal with specific type of data structure or non-structured data. And this had one new step of complexity. And sometimes it's quite difficult to ensure a good data quality. Of course, we have some problem around the scalability, because to be able to train this model, all methods need to be very efficient and well adapted for distributed and parallel environment. And also, sometimes it's quite complex to find a good balance between the accuracy of the model and the efficiency, so the cost needed to train this model. So this different challenge need to be taken into account in this thesis. So the main objective of this thesis is to reduce the model cost associated for the training and the inference. So for that, we have three main parts on which we will work. The first one is the compression of the model. For that, we will try to reduce the model size. We will also attack the data. We will try to improve the data quality to help the processing of this data. And of course, we will take care that whole new method are well adapted for distributed and parallel computing. In this thesis, we mainly focus on the pre-processing part here. This means that we will work we will transform and build new methods that will be applied on data before it was given as input to the model. And we ensure the data processing. Then for that, we also try to use dimensionality reduction, and we make sure that we have good data movement and load balancing. So to achieve our goal to reduce the model size, we improve the data quality. For different contributions, focus on different type of data structure, which are all sparse data. In the first part, we will see the data structured as graph that we use on GNN, graph neural networks. After that, we will see a sparse matrix representation of word corpus, and we will finish with a spectral embedding that use dimensionality reduction method to make a projection of data in a low dimension. And for each of these parts, we use spectral method here to ensure the quality of the data reduction. So I put my different contribution here, and this is in the cross of these three main domains. Okay, so now I will start with the data structured as graph, and we will talk about graph neural networks. A graph neural network is a neural network that is specially designed to process data structured as graph. And this type of structure needs to capture not only the information inside the data, but also the relationship between the different elements inside the dataset. Here we will focus on node-level tasks, because for this type of task, we have generally only one very large graph for the training. For example, if you want to make prediction about, you create a graph where each node of the graph is a human, and you connect them between if they know themselves in the real world. If you want to make prediction on this graph, you will only have one large graph that would be used for the training. And in GNN, the structure of the graph is used to control the propagation at each layer. Here we use the adjacency matrix, which is the matrix that represents the structure of the graph, to control how the information will be propagated. Exactly. So the graph structure play an important role in graph neural networks, and it controls how the information propagates. So modify the graph will also modify how the information will be propagated inside the graph. And the problem is that when you have only one graph for the training, the model will only train with this specific graph, and after that, it will not be able to generalize for other graph that that can be used for inference. And one solution proposed in the literature to reduce this lack of generalization is, at each epoch of the training, we will build a subgraph from the original graph to be sure that the model will learn on different subgraphs. But the existing solution removes some part of the graph completely randomly, and so nothing ensures that the new generated graph is consistency. The new graph structure is consistency. So this is why we propose ranked drop. The goal of whole method is to create a subgraph from the original graph, but base it on the we will extract some topological information to construct this new graph to be sure that this subgraph will have a similar structure than the original graph. For this algorithm, we have three main steps. The first one is to extract information from the graph. After that, we will build a selection probability and build subgraph. We will see each step one by one. So, yeah, the first step is to extract information from the graph. So for that, we will extract some topological information from the graph in a different way. We can use different metrics to extract the information here. And the idea is when we have extract enough information, we will fusion this different information to create a final score. And this final score, one score will be attributed at each node of the graph. And the idea is that this score will represent the importance of the node inside the graph structure here in this graph. So the idea is a node is important in this graph, the higher the score will be here. When you have a final score for each node here, you will we propose to use a scan wizard method to transform this score here in a selection probability where we will give at each node as a probability to be selected to build the new subgraph in function of its importance inside in function of the score here. And we propose to use scan with that function to transform this vector to a selection probability. And when we get the selection probability for a whole graph, at each epoch, we will build a new subgraph from this selection probability. We will select one node in function of the probability here. And when we select a node, we will select a new edge randomly. And we will add it into the new subgraph. And we will restart this step until the size of the subgraph is enough for us. And at each epoch, we will restart to build a new subgraph. So to be able to compare whole method with the totally random dropping, we have this experimental protocol. So the two information that we extract from the topological information of the graph is first the payload score. This score will give us an idea of the importance of each node in the global structure of the graph. And we also use the node degrees to represent the local importance of one node, because as I said, the information is propagated between neighborhoods. So the most a node will have degrees, the most it will have a local importance. We compare with three different datasets here, and for each, this is the same dataset that was used in the paper that introduced the totally random dropping. Okay, so here we will see the impact of dropping on the training. We can see in blue the loss curves when we don't have any dropping. In orange, we have with totally random dropping, and in green, the loss curve with whole dropping. And we can see on this Cora and Seitzer dataset that applied dropping have an important impact on the loss curves. Here we can see that we have better loss curve when we apply dropping. So for the training, it have an impact. And now we will see together the impact on the accuracy, and we will test the scalability. So for each dataset here, we apply GCN with different size, with different number of layers here, and we compare the different accuracy here that we can have without any dropping, with totally random dropping, and with whole purported method for dropping here. So we can see that globally, I need to precise that we don't do any hyperparameter tuning. We use the same hyperparameter than the one defined in the random dropping paper. So for each dataset, for each method, we see that dropping helps to have a better accuracy than without any dropping. And it's very important when the number of layers become important here. For example, without dropping, the accuracy is only close to 30%. And with the dropping, we can improve by more than 2 times the accuracy here. And it's also, we can see here with Seitzer, here between no dropping and with full dropping, we increase the accuracy by more than 50%. Okay, so this is the impact on accuracy. And now we also see the portability of our method. For that, we apply whole dropping method with different type of GNN here, and we compare the accuracy here. Also here, we don't have any hyperparameter tuning, and we can see that dropping helps to improve the accuracy, and we are able, without any hyperparameter tuning, to have approximately the same result than random dropping. So yeah, a good dropping helps to improve the accuracy of the model. Okay, we are finished to focus on graph data structure. Now we will see a matrix representation, the co-occurrence matrix representation that is used to represent a corpus of words and a corpus of sentences used in a natural language processing. Okay, so a co-occurrence matrix is a matrix representation that gives us information about the relationship between the different items inside the dataset. Initially, this type of matrix was used to visualize the co-citation inside the dataset, but after that, we also use this type of matrix in other tasks, for example, to finding its association, to identifying pattern, or to get similarity measure between different elements. And more recently, we also use the co-occurrence matrix in deep learning, and it have an important role for word embedding. For example, the proposed method GLOVE in the literature use a word-word co-occurrence matrix to create an embedding of NLP dataset. So for example, this GLOVE method helps us to reduce the input dimension, which is around the number of English words inside the English vocabulary dictionary, which is around 400,000 words, and it creates an embedding, a vector, a representation of this in only 300 dimensions. So to create the co-occurrence matrix, it's possible to create a co-occurrence matrix thanks to a multiplication between the transpose of the incidence matrix times the incidence matrix. I put an example here of corpus. Here we have an example with 3 sentences and 5 different words inside our dictionary. The idea is that we will associate for each word an index here, and we will create a representation of each sentence of the dataset as a vector when we will add 1 when the word is inside the sentence. Yeah, like here we have the word like in the first sentence and in the second. So like is the fourth one. So we have like everywhere. And so this helps us to create the incidence matrix. And thanks to the equation here, we will be able to build the co-occurrence matrix. But this incidence matrix have 2 main data specifications. The first one is here that we have only Boolean nature of data. The matrix have only 0 and 1 element. And we also have a sparsity of data here. Here it's a sparse matrix. It's not very clear here because we have a small example. But when you have a very large dictionary here, the size will be very large, and you will only have something like 10 or 20 words inside each sentence. So you will only have maximum 20 non-null elements on each vector. So how we can take advantage of this both specification of the data? So to take advantage of the sparsity, we can use the sparse linear algebra. And so this is specific data structure that can be used to take advantage of the high proportion of 0 element inside the matrix. So use data star storage is more interesting when the density of the matrix is low. The density of the matrix is the number of non-null elements on the total number of elements inside the matrix. So when the density is low, we can use sparse storage format to create a representation of the matrix. I put an example here, and we will compress with LPAC format because this is specific format that is well adapted to understand how we will build the covariance matrix. So here I put an example here when we have several non-null elements, and the idea of page of LPAC is to push all non-null elements to the left and to store in one matrix the value of each non-null element, and in the second matrix the index of each non-null element. And from these two information, we was able to rebuild the original matrix. So yeah, the idea of LPAC is to compress the matrix by row. We will compress all non-null value by row. So this helps us to take advantage of the sparsity. And to take advantage of the Boolean nature of the data, we can use the sparse pairwise the pairwise approach. In this approach, the idea of this approach is to try to find all pair of non-null elements inside a data set to create a matrix representation of each sentence in the corpus. So let's take for example the incidence matrix of the previous example here. And so for each vector here, we will try to find all pair of non-null elements where we have non-zero element. For example, here we have the orange and the green one. So we will turn 1 for each pair where the two elements are true together. And we do that for each vector. So for each vector, we get a first matrix. And thanks to a reduction, we can be able to immediately have the co-occurrence matrix here. And so we proposed a new method named sparse pairwise, which take advantage of both the Boolean nature of the data and the sparsity. So for that, we will first go from the incidence matrix here. We will first compress each each sparse row to the left thanks to LPAC format. And after that, instead of finding all pair of non-null elements, we will associate each non-null element with the compressed vector. So we will have less pair here to find. And thanks this, we will be able to immediately build the co-occurrence matrix faster. Okay. So this is the idea of our method. So to be able to compare this method, we build a theoretical complexity analysis between the different approaches. So here, for dense, we have a dense matrix multiplication, sparse matrix multiplication, the pairwise approach, and the sparse pairwise approach. And we compare for all these different methods, the time complexity and the memory complexity. For that, we use the BSP approach to compute the time complexity. But here, for each method, we only have one superstep. So we don't have a difference between for synchronization between the different methods. So we can, and also the communication for this type of method is only used for data distribution, and we don't have no communication are needed to get the co-occurrence matrix if the data are well distributed between the different nodes. So the time complexity in our case is equivalent to the computational complexity here. And so we have put here the different time complexity in function of the method for each method. And we can see that the only sparse pairwise approach have a complexity between the density square. And since the density is between 0 and 1, and often it's more close to 0, in theoretical, it's more interesting to use sparse pairwise approach when the density of the matrix is low. And moreover, because we also compress the data, each row, we take advantage of the sparse storage format on the memory complexity with the sparse pairwise approach. Okay, so to be able to validate this theoretical analysis, we have created a corpus generator, and where we can be able to make variation in different parameters to control the size and the density of the generator. And we use the Rush cluster. We use up to 25 nodes of the root cluster, and this gives us access to 1,000 core to realize for experiment. And so we will make some experiment in function of different parameters to validate the theoretical complexity. So we can start with the density here. Here we have the different the execution time in function of the approach, and in function of the density here. We have here the density between 10% and 90%. So here we are very close to a dense matrix. And here we have a zoom between 1% and 9% of sparsity. And we can find here the D square theoretical complexity for one method and the D for the other method. Here, of course, when you have a dense matrix-matrix multiplication, the density don't have any impact of the execution time. So this figure helps us to reflect the theoretical complexity we got in the previous slide. Okay, so now we can try to make some variation in the size of the data set. So that for each method, the complexity in function of the number of sentence is linear. So to compare the different approach, we multiply the number of sentence by 10, and we try to see how many time is needed to compute this new sentence for each method. And so here we can see that thanks to the coefficient here, that with sparse pairwise approach, when we had one new sentence in the dataset, we need the less time to process this new sentence compared to the other method. And we do the same thing with the different size of features, the size of the dictionary, and we make some variation between 10,000 to 100,000. And also we have for each method yes. We also try to compare the different strong scalability between the different approach. And as I said, the communication is only needed for data distribution. We don't have any any communication inside to build the co-occurrence matrix inside the method. So the efficiency is very important for each method. And so adding one new core to parallel the co-occurrence matrix computation help to have a significant impact on the execution time to build this matrix. And yeah, the efficiency is close to 100%. Okay, so all this result was get with our corpus generator, but we need to also compare with real-world data set to be sure that we have the same result. So for that, we use 3 different data sets with different size and different density. This means that the matrix is very sparse here. The first one and the third one is very sparse. And for each of these data sets here, we compare the execution time needed to build the co-occurrence matrix with the different approach. So we see that sparse pairwise is the most interesting to compute the co-occurrence matrix with each data set. And the factor is directly correlate with the sparsity of the data set. The most the data set is sparse, the most it's interesting to use the sparse pairwise approach. And moreover, because we take advantage of the sparsity of the data, we are able to compute sparse, very important data set, very large data set, where we have an out-of-memory error with a matrix that don't take advantage of the sparsity. Okay, so we have here we have see how the co-occurrence how we can build the co-occurrence matrix. The co-occurrence matrix is a representation of word corpus, and now we will zoom out a little bit to see together method around the embedding initialization. So I need to first introduce what is an embedding. So an embedding is a process that is used to represent data that is built on with a specific structure, with a non-classical structure. And the idea of embedding is to be able to have a vector representation of this data in a low dimension and dense with all elements in the vector would be numerical value. So the embedding layer is between the data set and the deep learning model. And the idea here is to, the output of the embedding will be given as input to the rest of the model. So it's important to have an accurate embedding. It's important to keep enough information here to help to give to the model and give it to the model to be sure that the model will be able to generalize and to make a prediction. And so of course, embedding, if the embedding is not well defined, it can cause some data consistency issues, and this can slow down the training of the model. So the question can be how we can build an intelligence initialization to have a consistent embedding. So to build an initialization of embedding, we propose to use eigensolver to extract dominant eigenvector of a matrix representation of the dataset. That can be, for example, the cochrane matrix that we see in the previous part. And we will, from this matrix representation, we will use an eigensolver to get the dominant eigenvector. And after that, we will use this eigenvector to initialize a first embedding to be sure that the output of the embedding will immediately have a consistency from the original data. And after that, we will give it as input to the rest of the model. So, of course, we cannot extract the dominant eigenvector on a rectangular data set. So this is why we need to find a sparse, a square matrix representation of the data set. So for example, the cochrane matrix here. And we apply an eigensolver. I put Miramenes here, and we will discuss why I choose this eigensolver in the next slide. And this eigensolver will help us to extract the M dominant eigenvector. And after that, when we get this eigenvector, we will take the original data, which is represented as its own structure, and we will use this dominant eigenvector to have a projection of this data in a low dimension space M of numerical value. And this is this vector that will be given as input to the model. And why we use dominant eigenvector? We use these vectors because this ensures that the variance of the projection of the original data is maximized in this new dimension representation. Okay, so we propose to use Miramenes for has eigensolver in our case. Miramenes is an extension of the original IRAM method, which means implicitly restarted Arnoldi method. The idea of this method is to find the to answer sparse and large eigensolver thanks to an iterative way. And it's based on the Arnoldi method and include, instead of give new space for finding at each epoch to restart, we will use implicitly restart mechanism to improve the efficiency and the convergence of the method. But the original method only search the solution of our problem in one preload subspace. This is why we propose to use Miramenes, which is an extension. And in this method, we will search the solution in several subspaces that are nested. And the idea here is that we are able to deal with matrix where the eigenvalue are clustered or very close together. We have some cluster of eigenvalue where IRAM don't converge to the good solution, to a correct an efficient solution. So Miramenes ensure a good stability because we can use it on different type of matrix, and it's more general than IRAM, and it's also ensure the scalability because the method is well adapted for a distributed environment, and we can also use it for very large eigen problem, which is well suitable for massive models. Okay, to experiment for this proposition, we will separate our experiment in two main parts. And on the first time, we will evaluate the IRAM and Miramenes scalability For that, we will try to use it with sparse and dense matrix and see the impact of each method on the execution time when in function of the size of the model of the parallel environment, the number of core used to find the eigenvectors, the dominant eigenvectors. And after that, we will apply this spectral embedding on a real deep learning model, and we will see the impact of this embedding on the accuracy of the model. And we will show the interest of using a coherent embedding to represent the data and prepare the data before give as input to the model. Okay. But first, we will compare the MIRAM and IRAM implementation. Here we are in function of dense matrix and sparse matrix here, and we compare MIRAM implementation and IRAM implementation. So we can say that we have find a dominant eigenvector with MIRAM and is well adapted for a distributed environment when we increase the number of processors. But we can see that the IRAM have a more important speedup. And this is because MIRAM need to explore the different subspace, nested subspace. And this exploration of nested subspace can only be done on a sequential way. So this has an impact on the speedup. But yeah, the execution time, when we have enough computation core, it's the impact is relatively low on the execution time. And here we have make the same. We are trying to find the eigenvector with a sparse matrix here, and we can see that take advantage of the sparsity of the data have a very important impact of the execution time. And so, in case of deep learning dataset or other type of dataset, or often sparse, and so use this matrix is very interesting in this with this data specification. Okay, so now we will see the impact on accuracy of the model when we use an embedding based on a dominant eigenvector. So to be able to compare the different approach, I built different model here with different size of the model. And the idea is that for the large model, we have more parameters than for the other one. And we define a different size of model. And we will compare in this figure here the difference between the accuracy without any embedding. So it's the line here in the color here, with orange the large one, the green the medium one, etc. So we compare here, the line is the accuracy without any embedding. And here we have the accuracy when we use an embedding, and the curve represents the accuracy with different size of embedding dimensions. So here is the number of eigenvector used to create the representation of the data of the embedding data. And we can see on this figure that with accuracy, when you had the number of eigenvector to create the embedding, the accuracy increase. But when you have enough information to represent the global importance of the data, the accuracy is approximately the same when you add more embedding dimension. And also, you can see that with a smaller model here, you are able to have approximately the same accuracy with the blue model, the low model. With an embedding, you are able to have approximately the same accuracy than with the large model without any embedding. So this shows that the low model is approximately 10 times smaller than the large one. So this means that use an eigenvector-based embedding, and so that we have a coherent embedding, and help us to have approximately the same accuracy with models that are smaller, with that 10 times smaller. Okay, so I presented all my conclusion, and now it's time to conclude. So, in this presentation, I present a first efficient dropping method for GNN This method ensured the coherence of the graph and increased the accuracy by up to 50% compared to no dropping. We also proposed a new fast approach to build the co-occurrence matrix, which is used to represent a large language model corpus. We take advantage of both sparsity and Boolean nature of the data, and it's go up to 34 times faster with real-world dataset Cassandra real-world dataset. And finally, we also introduced a new spectral embedding method that uses eigenvector to create a coherent embedding initialization. And we show that this type of embedding, which ensure a high data quality, help us to have similar accuracy with model 10 times smaller. I also, during my thesis, I also work on something else that I don't really add in this presentation. We define a new data distribution for a sequence of sparse matrix multiplication, which is a very common operation in graph neural networks. And whole data distribution presented here ensure that we have a good load balancing, and also we avoid all-to-all communication when we realize the succession of matrix multiplication. Okay. As a final conclusion of this presentation, we show that we have improved the quality of the data in the pre-processing part. So before to give this data as input to the model, and we improve the quality for different sparse data representation, and we ensure that we keep enough information for the data to be able to make this prediction. We also we reduce the data dimension, and we ensure that this retain enough information for the training, thanks to spectral method with PageRank in graph neural networks, and with eigenvector for dimension reduction. And we also demonstrate that a good pre-processing have a significant impact on the model accuracy. So and of course, we ensure that all whole methods are well adapted for distributed and parallel environment. So the general conclusion of this talk is that the quality of the data representation has a major impact on the accuracy and on the performance of the model, and improve the quality of the data can help us to have better accuracy with all deep learning models. Okay. I will finish with some perspective of my work. The first one is to extend. Here we have only focused on the pre-processing of the data. And one interesting perspective can be to extend our work on different parts of the model. For example, at the post-processing. So after that, to have a better visualization of full data, of the prediction of the data, also inside the model to improve the intermediate data representation, for example, with the transformer the model. And also we can generalize this type of method. We can use different specification to improve whole model compression method, whole data compression method, by continue to take advantage of specification of the data, like sparsity, Boolean nature. We can also define new algorithms that take advantage of the mixed algorithm to reduce the computational time complexity to get the result. And also we can try to improve this new algorithm to be sure that they're well adapted with AI hardware, a specific architecture that at the moment are more well adapted for dense operation. Okay, thanks. Here is the list of my publication. Thank you for your attention, and I'm waiting for your question.